Hello and welcome to this final screencast on solving the Sudoku. Here we are tasked with improving the code a little bit and sprucing it up and adding an additional functionality that the diagonal of the Sudoku should be unique. The principal diagonal that runs from left to right, left topmost left corner to bottommost right hand corner, and the secondary diagonal topmost right corner to bottommost left corner. Both the diagonals should also contain you should contain unique elements. So, well, let me show you how I've gone about solving that. So this is the code that was forwarded to us by Dr. Peter Norvig. As you can see, that's quite a lot of code, if you will. So, um, yeah, see, so it starts from our main method, if you will. So we don't have a main method per se. It's all inside the main. Okay, let's see. So we have this grid 2, that grid 3, that's what we are interested in solving in. This pretty much works for every other Sudoku, I guess, but for the sake of simplicity, let's assume that we are trying to solve this grid, and that's about it. So we have to first parse this grid and construct our cross product uh, matrix first, and then compare it with this and fill appropriately, and then check for any errors, whether there are any errors while we are passing the grid or not. So for that we have the cross, and this is going to print the cross product, and here we have a, b, and 1, 2, and all of the things, and we then zip all those together um, to get a key value pair of the Sudoku and the grid and whatnot. So here, these are the two changes that we have made to this code. So we have actually got an array or list, if you will, since this is Python. If you want to be real stickler for the nomenclature lexicon. Alright, so here we have all the row column notations for the principal diagonal and the secondary diagonal as well. So we are going to include this for that, and cross of that, cross of this, plus the diagonal 1 and the 2, right? So when we are constructing, we are also adding a constraint that it should be at the diagonal should also be unique value, if you will. So if we just add those values and make our grid and try to solve that using our depth first search algorithm recursively, backtracking if needed, wherever needed, I think that's about it. That's how you solve the code. And let me just quickly run this and show you. See, so this is our grid that we have constructing out of our diagonals, and what actually this is the input for the previous list of lists, if you will. So just ignore this portion, let's look at this. So this is our input. Let's look at the grid and let's look at the output is generating. So this is grid 3. So this is dot 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 6. So first three elements are empty, followed by another empty and a 6, and the remaining dots. So that input is fine. So remaining you can trace for other. So the grid is finally constructed in a good way, and let's look at the solved portion on it. And it if you look at it, this just took only 0.01 seconds to solve it. So if you look at the diagonal 3, 9, 6, 7, 2, 8, 4, 5, and 1. See, all the values are 7, 2, 8, 4, 5, and 1. All the values in the principal diagonal are unique and are between 0 through 1. And let's look at the secondary diagonal. 5, 6, I'm sorry, just 5, 1, yeah, 5, 8, 7, and then yeah, the second grid here, 6, 2, 1, 3, 4, 9. So if you will, we have successfully solved the conundrum of having our diagonals to be unique, and that's all I have to say about it. Thank you.